So we will actually state the mathematical problem for that. So we'll again consider the same nonlinear dynamical system. Here we're going to specify the cost of a specific form, and this is a very generic form. There are two parts of it. I mean, here there is an initial time and the final time. The final time may be known in some cases. Sometimes we want to leave it free, but we could actually have a terminal cost to be minimized. Maybe at the end we will actually get a reward, and that could be a negative cost to be minimized, right? Or there is a serious cost involved at the end. But on the other hand, there could be a running cost, which is what is the integral denotes, right? So the running cost or the terminal cost, basically the terminal cost is at a final point and typically may not depend on the final value of control, whereas the running cost will certainly depend on u. So basically the problem of optimization here is find, if it exists, u that minimizes j. It's as simple as that. So the solution depends on this very strange quantity called Hamiltonian, and there are historical reasons why it's called Hamiltonian, because eventually when we'll see the answer, it's closely related to the way the mechanics solution that yesterday I was talking about principle of least action. The solution to that particular problem looks exactly the same, and therefore the terminology coming from mechanics is what we use. So this is nothing but this L, right, the running cost, plus something to do with your dynamics F, and an additional parameter lambda, right? And as we will see in the proof, basically this lambda is coming from the Lagrangian parameters, the Lagrangian multipliers that we were talking about due to some constraints and things like that. So what is the solution to this particular problem? And I will definitely show you insights into the proof of this particular problem, but the solution turns out to be quite interesting, right? So these are the necessary conditions. You can have second order necessary conditions and sufficient conditions also, which we won't show. Like I keep repeating myself, basically most of the time we set the first derivative to 0 and then hope that basically the answer will tell us something about whether it's minimum or maximum, and maybe there are very few of them and things like that, right? So, and if you're dealing with convex problems and things like that, basically you'll end up with a global minimum anyway, right? So that's why most of the time first order necessary conditions are good enough to solve. So anyway, the necessary conditions are something like this. X dot is basically partial derivative of h with respect to lambda, and let's take a look at that. So if you look at this Hamiltonian function h, if you take partial derivative with respect to lambda, that will give you f, right? X dot is equal to f. So there's nothing new that we are getting from this particular first equation, but it's nice to state in terms of this Hamiltonian. But the second and third are the ones that we get from the optimal solution that we derive, right? And the first one is lambda dot is equal to minus of partial of h with respect to x, and then the last one is 0 is equal to partial h with respect to u. So look at the structure, and then we will talk a lot about this particular solution. You have this x dot is dependent on partial h with respect to lambda, and then lambda dot is minus of partial h with respect to x, and they are closely related, but the sign is changed and things like that, so they are like adjoint to one another, and this is a very standard thing in many optimization problems and we see that there. The second aspect of it is, so the primary variable is u, okay, but x depends on it. So there are multiple ways of solving this particular problem. You could actually go back to the basics, and just the way we solved our calculus of variation problem, we could try to introduce perturbations of u and then see the effect of those perturbations on x, and then derive these equations. So that's one way of it, looking at it. The second way of looking at it is try to convert this into a unconstrained problem by treating this x dot equals f as a constraint. And here I am not even putting any other constraints like the cu, the the script u set in terms of putting constraints in that, we ignore that, u is basically anything beyond the fact that basically x dot equals f, right? So all these methods are valid. Now in addition to this, basically there is another variation equation that has to be satisfied, and then we will discuss that when after we see the problem derivation of this particular problem. So we have x dot is equal to f of t comma x comma u, right? And the cost function is basically x1 t1 plus integral of 0 to t0 to t1 of L of t comma x comma u dt, right? So like I said, we can treat this in multiple ways. I'm going to treat in one specific way, basically construct a Lagrangian, and for sake of simplicity, I'm going to ignore this, and there is a specific reason for that. I can always include that as part of L by realizing this w can be written as integral of wt t0 to t1. So this is d by dt of w, right? dt plus w of x0 comma t0, right? W is proper function and things like that. So but then this is nothing but a partial with respect to t plus partial with respect to x times x dot, right? And then you have integral. So w, therefore, other than this particular constant which we can ignore, we can treat j hat to be j minus that. Basically we can include this part into this integral and then basically solve that particular problem. So I'm going to ignore that aspect and then simply consider j to be that integral, and therefore I'm going to consider the Lagrangian. And if you recall yesterday, the Lagrangian is going to be, I'm going to write it and then explain. So t0 to t1, okay, L of t comma x comma u plus lambda transpose, okay, x dot minus f, because that's the constraint we have, okay, and dt. So this is still L of u, so to speak, but we actually, since we are treating x as a variable, so the Lagrangian of this particular thing is basically, it's going to depend on x, x dot and u, okay, could depend on yeah. So this is what we want to minimize unconstrained, right? So if you recall, I don't know, call this L tilde or something like that, and the Euler-Lagrange equation, the optimal necessary, the first order necessary condition or extremal condition for solving this particular problem with as an unconstrained problem, unconstrained because we converted using Lagrange parameters, becomes something like basically this: partial as L with respect to x minus d by dt of partial with respect to x dot is equal to 0, partial L with respect to u minus d by dt of partial with respect to u dot, okay. And so when we do that, let's see what happens, right? So before I do that, so I have this lambda plus lambda transpose times x dot minus f. Let me actually do this slightly different and then put a minus here. I can certainly do that. There's nothing wrong in that. I can put any sign I want, right? So let me rewrite this. So I have my L tilde to be equal to L plus lambda transpose F minus X dot, which is nothing but the Hamiltonian the way I defined minus lambda transpose X dot. Okay. So yeah, this should be simply U. So basically, when I use this, what did we call them? Sorry, this should be L tilde everywhere. We call this Euler-Lagrange equation. So first part is basically take this partial h with respect to x minus d by dt and partial of this L tilde with respect to x dot, which is going to be L transpose, right, with a minus, and then basically we get a plus, and then that is going to be equal to 0. So that's the first equation, right? The second one is basically partial with the, so the first equation it comes from taking the derivative with respect to x and x dot, and the second one is something to do with u. Notice that there is no u dot in any of these things. Basically you will end up with partial h with respect to u. In reality, this is an unconstrained problem. I should have specifically also mentioned lambda there, and lambda dot is, I mean, when you take the derivative with respect to lambda, there's no lambda dot, so you'll get another equation, partial h with respect to lambda is equal to 0, but this will get us back x dot equals f, which happens to be L tilde with respect to lambda, and which is nothing but partial h with respect to lambda, right? So what we have seen is basically by treating this problem, right, as a constraint optimization problem and solving it using Euler-Lagrange equations coming from calculus of variations, we get these three conditions in terms of this beautiful function called Hamiltonian, and this adjoint equations x dot and lambda dot are the ones that we see typically, momentum and then position equations and things like that. The last equation, we totally ignored is whether T1 is specified, whether x of T1 is specified, all those kind of things we ignored. And if we assume that they're all given to be chosen, then this equation needs to be satisfied. Now this equation has to be understood in a very specific manner. Suppose if you were to have a problem where basically delta T1 is T1 is fixed, then delta T1 cannot be anything but 0. So this part is not going to matter to us. But whereas this one, on the other hand, delta x1 is arbitrary in that particular case if it is free to choose. So we will end up with partial w with respect to x minus lambda T1 is equal to be 0, right? So similarly, both are free. This one is 0 and this one is 0. Right. So that's how one can apply this particular technique. So maybe I'll show you how to use this particular technique to solve one simple problem. I'm not going to solve, but more importantly, I'm going to set it up, right? So so I have this state space equation, x1 dot is equal to x2 and x2 dot is equal to minus x2 plus u. Okay, if you're wondering, this basically is same thing as x double dot plus x dot is equal to u. Okay, and what kind of equation is this? Basically, this is a free body that's moving through space with some damping factor assumed. Okay, so I want to control this particular system, and with the cost basically from T0 to T1 only cost that I'm interested in minimizing is half u square, and then we will assume basically the final values are all given, right? So nothing else is there. So what is the Hamiltonian? Hamiltonian, if you remember, is nothing but L plus lambda transpose x dot minus f. Plus lambda transpose f. Okay. So in this particular case, this is going to be half u square plus what will we get? So we have lambda 1 x2 and plus lambda 2 times minus x2 plus u, right? So that's the equation. And now we don't have to worry about the x dot equation because we already have that. Lambda dot equation, okay, lambda dot is supposed to be minus partial h with respect to x, okay. So what does this mean? Lambda 1 dot is partial with respect to x1, and that's 0, right? And lambda 2 dot on the other hand is partial h with respect to x with a minus x2 with respect in this thing. So what will I get? I will get minus lambda 1 plus lambda 2, okay. So and you can solve this, but for what condition is the question. Basically you can convince yourself depending on which free cases there will get some boundary condition. Let's say I don't know, we will say lambda 1 of t1 is equal to lambda 2 of t2 is equal to 0, and I'm not paying particular attention how I'm going to get that, but so that can come through the boundary through the final conditions and things like that. Now there's a third equation which says the partial h with respect to u is equal to 0, which is essentially 2u plus lambda 2 is 0. So therefore u is minus half lambda 2, right? So more or less we solved, right? Lambda 1 is some constant, right? Lambda 2 is going to be in terms of that constant and the final value, some value, and then u is solved, right? And then of course we have this x dot, and then substitute u, and then you'll get the closed loop system, right? And this is supposed to be the optimal solution. Hopefully it's really the minimum solution. But one observation that one has to make. So remember that x dot is basically you have f of t comma x comma u with some initial conditions, right? Something. Whereas the lambda dot equation, whatever it is, you have final condition, okay. Typically, I mean, that's how it is going to be. You can solve for u and things like that, but the fact that basically you have this very strange set of differential equations, part of it is with respect to initial condition and part of it is with final condition. So if you knew lambda of t0, then we could actually run this simulation, right? But on the other hand, we don't. So typically how they solve this particular problem is basically they guess some lambda, and then basically they'll see whether it reaches lambda of t1 or not, right? And that's called a shooting method, because you're kind of shooting in the dark and then hope that you'll reach lambda of t1. Now, believe it or not, when you actually solve any problems related to space shuttle going from Earth to some other planet or some other point in space, this is precisely what people do in terms of solving. And then any expert who solves this path planning for these space shuttle missions essentially are solving these shooting value problems. And if you recall, if you have seen the movie Hidden Figures, you will actually know that these were calculated without computers, but actually human computers, and typically they used women at that time. And the movie is all about a particular, eventually to be scientist, how she got into the mathematics and physics of it, and not just being some calculator for solving some numerical problems, right? So, so that's the technique of optimal control problem, unconstrained case. The constrained case is more difficult, and basically, well, it's not, so suppose if you have an inequality constraint, you can still go back and basically do the same thing that we have done just now by adding more Lagrange multipliers and things like that. But for very specific problems like the control being between say two values and things like that, there are specific solutions, and very famous solutions too. But otherwise, numerically one can solve these things these days without really a lot of problem, especially with huge computing power. We can do a lot of things, right? So I'll just want to demonstrate this particular solution on very standard problem of linear systems, and then we're going to go time varying because it doesn't pose extra difficulty in this particular case. And we will consider quadratic costs, linear, quadratic, those things are the ones that are typically we will consider when it comes to linear problems, and without questioning for the timing, we'll consider that, right? So let me put it this way: quadratic is the kind of the lowest power that we can think of, which will give you non-negativity, and that's a nice thing, right? So I could have taken a square root of the quadratic, but then that poses a different kind of problem. So typically we minimize quadratic objective functions because they are differentiable and they're nice and things like that. They're easy to solve. Anyways, so in this particular case, the Hamiltonian is simply x transpose qx plus u transpose ru plus lambda transpose ax plus bu. Just again, going back to your cost function, as you can see that this cost function is picked in certain way that it weighs both the state and control, right? If you just have the control weighting, like in the previous problem that I showed, half u square, what's happening is basically we're going to say we don't want to spend any time. That's like a minimum fuel type of problem, which means the state could be going far off before reaching its destination, things like that. So it makes sense to have both of them, both of the elements in the cost function, right? Whether you have terminal or not, it doesn't matter. So anyway, so the solution, therefore, basically when you actually plug into this Hamiltonian equations that we have, x dot equals partial h with respect to this thing, lambda dot and things like that, we'll end up with this quite interesting solution. And look at the compare the x dot equation, which is a x plus bu, and the lambda dot is minus a transpose lambda minus 2q times x, right? So this a and a transpose with a minus is what I'm asking you to pay attention. And then there's a final condition, lambda of t1 is equal to w of x t1, w times x t1, and that could very well be 0. But the nice thing is basically you have a solution for your control, which is minus r inverse times b transpose times lambda, and lambda is coming from here, right? So this is actually the famous Kalman controller, Kalman regulator, linear Kalman regulator solution. And interestingly, even if you have white noise and things like that, this particular solution has certain interpretation in terms of minimizing H to norm and things like that. Okay, so that is essentially optimal control, open loop control through our calculus variations approach. But there is something that was discovered by Kalman himself again. Somebody else, not Kalman, Bellman. Something called principle of optimality, which we will see in a second, and he called that dynamic programming. And Bellman is one of those very interesting character who finished his PhD in 9 months or something like that. Not many few pages apparently in his dissertation and things like that. He solved basically essentially this dynamic programming problem in both discrete time and as well as continuous time. It's quite easy to understand in discrete time, so it is in continuous time, but the mathematics becomes slightly nasty. So anyway, the cost function is same, but let's first look at the intuition first, right? I want to minimize this j function, right? I'm explicitly writing that it is could be dependent on u, t0, x0, right? Maybe we don't have control over t0 and x0, but it is a function of t0, x0 and u, right? Once u is known, t0 is known, x0 is known, x dot is going to be known, and then rest of it can be evaluated, right? So that's the assumption. Now let us somehow figure out that we have we have a solution. Then what can we say? What we can say is basically on the path, it's something like this. Let me actually draw a picture and then basically demonstrate dynamic programming principle. And then, so I have this point and this point, and somehow I know that this is the optimal path, right? Principle of optimality at a very high level says that if I pick an intermediate, right, this is t0, t1, and then let's say this is t, somewhere t belongs to t0 comma t1, right? The optimal path from this particular space at that particular time, okay, the optimal path between t and t1, x of t and x of t1 at that particular time is going to be the same thing, right? And fairly obvious. Suppose from this point, if there is something other path that is going to be better than this particular part, what that means is I could have actually gone through the same point and then gone through the second path and then got a better solution. But the original assumption was basically this is your optimal path, so this cannot be optimal between these 2 points. Yes, if I pick some other point and then basically obviously that's going to be something very different, right? So but the principle of optimality or dynamic programming principle says that if you are on the path of optimality, from there you have nothing but just that path. Now that in itself, it's obviously not a big deal of an observation, though it is a very important observation. What Bellman did is he defined a value function that changes with time, and as you can see, basically he defined this v of t of x as the minimum value coming from solving the problem at some other time in between, right? And through dynamic programming principle or principle of optimality, we can write this v of t comma x is basically going to be infimum starting from that particular point. That's the definition. But from t plus t to t plus delta t, from there again you will have the optimal path, and you can take the infimum. So this is the so-called Bellman's principles of optimality. Essentially it translates what I just showed into mathematics of differentials, right? You can very well see basically once we see delta t, somehow we can figure out that there is going to be derivatives, and then basically one can sit down and derive essentially this beautiful equation called Hamilton-Jacobi Bellman equation. Why is it called Hamilton-Jacobi Bellman equation? This particular equation was realized in the different circumstances, and Bellman actually showed this in a very generic situation, and he called it principle of optimality. And then this equation comes right out of this interesting observation that if I am in the middle of an optimal path, from there is nothing but the original optimal path is the optimal path, and then by taking these small steps, we can actually get into derivatives and things like that, and we get this nice differential equation, right? So what does this tell us? Well, this basically tells us if I want to solve this particular problem, the value can be actually if you see this basically at t0 x0, basically it's the optimal value that we are looking for. At the final that's going to give me the final value. So essentially if I solve this differential equation where j doesn't appear, but anyway, if I solve this particular differential equation, partial differential equation, I get the value function, and that essentially solves my j, and then the x and u that's x that solves is the path that we're going to get, and you can back out u with a little bit of work, right? So anyway, I mean it's a very useful topic for one single reason. It's one of the most applicable methods in terms of your ability to solve nonlinear control. Well, what is not there is basically the fact that you don't have anything like stability and things like that. They are very sensitive to any uncertainties. But if you have a specific example where that's not an issue, then this is a beautiful approach to solve problems, right? And these are there are some wonderful books. Where, 3 of them are dated but reprinted, by Dover, Anderson, and Moore. It's a very classical book on mostly quadratic methods. It's a linear systems method. Athens and Falb is more generic, and my favorite is D.E. Kirk, written very well. And this more recent book by Liberzon is actually a very well written book, but it's quite dense in the sense that it's gets into the focus is more on the theory rather than how it is applicable to various cases, whereas Kirk's book is actually at the level of a master student or a PhD student. Okay, so that brings us to the end of the part 1 of this particular lecture, and we will get to the second part in a second.